Hello and welcome everyone. My name's Jennifer Saunderson and I'm your host for today's webinar. Thank you for attending today. Our live session is on the multi-core challenge, a practical approach to Cast-32A and AMC 20193 compliance, hosted by LDRA and SYSGO. Now I'll run over the agenda for today. First, we'll have our speaker and company introductions. Then we'll take a look at market trends and the challenge that multi-core presents, followed by the LDRA and SYSGO solution, the conclusion, and then onto our Q&A session. With that, Joe and Mark, it's over to you.
Thank you. Good morning, everyone. Good afternoon, everyone. My name's Joe Richmond-Knight. I've been a field applications engineer for SYSGO for about 6 months. A little bit about me. I'm based in the UK, near Reading. I'm a member of the IET, and I cut my teeth in embedded technology and its applications in the Internet of Things industry, so IoT, which instilled concepts of security, safety, and compliance, which I still use to this day.
Thanks for that, Joe. I'm Mark Pitchford. I'm a technical specialist with LDRA and have been for about 5 years. It's my second spell with the company, following up on 20 years or so as an FAE or similar, both here at LDRA and elsewhere. Before that, I spent many years as a software practitioner, mostly in engineering companies, working primarily in metrology, process control, and aerospace. I'd like to think that some of these things equip me to share some knowledge with you, and I've also made a few mistakes that hopefully you can learn to avoid from me too.
So a little bit about SYSGO as a business, founded in 1991 and originally a services company in the embedded market. SYSGO is the leading European RTOS vendor for embedded systems. We have a number of flagship products, including PikeOS, first released in 2003, which is a hypervisor and a real-time operating system. Ilinos, our first product, an industrial Linux distribution with long-term support, and more recently, PikeOS for MPU, which is compatible with lightweight systems that come with a memory protection unit only. We also provide board support packages, certification kits, and professional services, including product training and consulting. In 2012, we became part of the Thales Group. However, we've retained our brand and identity, and we operate globally and have local presence in Germany, France, the Czech Republic, and the UK.
LDRA has been around for coming up to 50 years now, which is a long time in the software industry, so we clearly do something right. As you can see, we serve the embedded software sector across the safety critical industries. The mainstay of our work has long been in the aerospace and defence sectors. These figures represent the certifications completed using our support packs, with countless others that used other verification approaches adding to those totals.
So collectively, we serve the following industries: aerospace, defence, medical, industrial and energy, space, rail and transportation, and automotive. A few examples of use in industry: within aerospace, our product PikeOS operates within the Airbus A350. In defence, PikeOS was selected as the OS of choice within the Airbus A400M Loadmaster workstation. Today, we're focusing on civil aerospace, for which DO178C, Cast-32A, and AMC 20193 apply, but many of the methodologies that we'll discuss today also apply to other industries.
Similarly, LDRA tools and services have been widely used across these safety critical sectors for many years. With such a long history in aviation, the list of projects that have involved LDRA tools and services as part of their certification efforts is quite lengthy. But for example, the LDRA tool suite was a test tool of choice for the Airbus A380, and that implied its use by the companies you see named around this image. Compared to a discrete multiprocessor design, multi-core processors offer a number of significant benefits, including performance due to the additional processing resource available, power consumption versus multiple separate single-core processors, form factor and size, and availability, given that the demand for single core processors has reduced in recent years. That being said, the use of multi-core processors increases the risk of interference between processing cores due to the shared resources. This interference presents an issue when designing a system that needs to be deterministic in its operation, which not only requires repeatable system output given a set of inputs, but also ensures that applications are executed within a given repeatable time frame.
Right, so the challenge then comes with the management of interference between these shared resources, which can include hardware components such as memory, buses, cache and I/O, as well as other software components like OS objects and services. On single core processors, interference risk can be mitigated by executing partitions sequentially, initiating some kind of cleanup operation during each partition switch. And although the same is often true for multi-core processors, parallel computing introduces another level of complexity that needs to be managed. So this is where Cast-32A comes into play. So Cast-32A is a position paper developed by the Certification Authority software team, CAST, which aims to provide guidance on the use of multi-core processors within the context of avionics and safety, performance and integrity. AMC 2193 is a joint effort by EASA and the FAA, which aims to supplement the guidance originally provided within Cast-32A. So EASA's AMC 2193 guidance is currently published within their wider AMC 20 document, and it's expected that the FAA will release their version of the guidance soon. As this new guidance was inspired by Cast-32A, there is a high level of commonality as well as a few subtle updates. So for example, dynamic allocation mechanisms are now discouraged by the new standards. However, they're still allowed given some valid justification. Definitions are provided for RTOS and Hypervisor components as part of a multi-core system. And an integrated modular avionics definition, IMA, has been provided, which includes robust resource and time partitioning criteria. For simplicity, we'll refer to this collection of guidance as Cast-32A. However, Mark will provide some more detail on the comparisons and subtle differences later on in the webinar.
So we've looked at the market trends, the problem, and now we move on to the solution. The joint solution between SYSGO and LDRA provides a framework of a rugged and safe real-time operating system paired with a suite of verification and validation tools provided by LDRA, ensuring that Cast-32A guidance can be followed and enabling product development to the highest design assurance levels.
So as part of that, now we're going to look at SYSGO's product solution and how it can be utilized for Cast-32A compliance. So an introduction on PikeOS as a product. PikeOS is our flagship product, which combines an RTOS, so a real-time operating system, and a Type 1 hypervisor into a single, highly portable operating system. It supports multiple guest operating systems that we refer to as personalities, including POSIX, ARINC 653, Linux, Linux, Android, PikeOS Native, and many more. Various applications can sit on top of PikeOS with mixed levels of criticality, which is achieved through our separation kernel architecture, supporting most popular platforms like x86, ARM, and PowerPC, to name a few. PikeOS is fully built in Europe and therefore has no export limitations and is ITAR-free. And finally, PikeOS is fully certifiable to the highest safety and security standards. PikeOS provides a modular certifiable framework, so the microkernel, the PSSW, the PikeOS system software, and the architecture support package, ASP, are available as pre-certified components. The platform support package, the PSP, is usually certified in the context of a project. We also have certifiable APIs available for a number of personalities, including POSIX and PikeOS Native, as well as a number of certifiable components, including certifiable file system, certifiable IP stack, and the certifiable math library. PikeOS Native, which provides a minimal C environment, can currently be certified up to DAL-A. In the case of DO178C for civil avionics, software can't be certified in isolation, so it must be certified as a full hardware and software stack. We provide certification kits, including the necessary artifacts and documentation, as well as support to fulfill the wider system certification requirements. So PikeOS is currently certifiable to the following safety standards: DO 178C for avionics up to DAL A, as I mentioned, IEC 61508 for industrial applications to SIL 3, ISO 26262 for automotive to ASIL D, EN 50128, 50129 for transportation to SIL 4, and of course is compliant to Cast-32A. For security, PikeOS has achieved Airbus SAR SAL 3 to 4, as well as recently achieving common criteria EAL 5+ with our PikeOS separation kernel 513. A little bit about our heritage then as a business and how this applies to safety and security. Over 75% of our engineering team have experience in certification, so it's a topic the team understands well. And this allows us to build certification kits and provide support in your wider product certification journey, as mentioned previously. So the big question, how does PikeOS achieve Cast-32A compliance? So the next few slides will demonstrate some examples of interference and how this can be mitigated within PikeOS. So firstly, multi-core processors. There is a risk of layer 2 or layer 3 cache access contention, which could, for example, be caused by the malfunction of an application running across one or many processors. This would primarily impact the execution time of running partitions, as the access to this shared resource could become either sporadic or limited. In a standard configuration, partitions of any criticality could be affected here. There are a number of possible resolutions to this within PikeOS, namely the division of cache between cores, so that the use of cache is separated into blocks per application. In the event of an application malfunction here, only the block of cache assigned would be impacted. Secondly, cache bandwidth monitoring could be implemented to allow for a malfunctioning application to be sanctioned in some way, which could include restarting or stopping the offending application. This could also, of course, be used in unison with the division of cache to further negate the impact of an application malfunction. Finally, cache coloring can be utilized at the PSP level, so the platform support package level, provided there's adequate hardware support within the platform. So in a similar fashion to cache access, system RAM also runs the risk of becoming unavailable due to application demand or malfunction. There's also a risk of overload due to hardware malfunction, abnormal I/O throughput, or a malfunctioning driver within the DMA or PCIe agent. The overload here would lead to a reduction in partition execution time, which of course may cause a major failure of a critical application. So within PikeOS, memory can be monitored and offending partitions can be managed to reduce or remove these impacts. In the context of DMA and PCIe, this could be extended to limit memory bandwidth if the monitoring system detects an overload. And a kernel level driver could also be implemented to monitor and control DMA requests to RAM. Virtual memory can be mapped to physical RAM blocks per partition, which can aid in reducing the risk and effects of interference through careful design. So another risk inherent with MCPs is that of an interrupt overload, causing the slowdown of partitions across both the core that is managing the interrupts and the other cores, where interrupts may be shared, for example. The cause of such an overload can reside within hardware or software, including abnormal interrupts generated by other hardware, but also throughout normal operation, considering most interrupt operations are asynchronous when compared to the rest of the system. Within PikeOS then, it's possible to implement an interrupt limiter, which reduces the possibility of spurious interrupts impacting the whole system. Time partitioning can also be utilized to ensure that interrupt intensive drivers can only execute during non-critical sections, for example. And you might be wondering what the picture is here. This picture shows the Apollo 11 lunar module, and of course, although not directly related to multi-core processors, at the time of writing, I was reminded of the famous interrupt overload that occurred during the mission, where the radar positioning system flooded the guidance computer with positioning data interrupts, causing, I'm sure, a number of nervous moments in the cockpit until a workaround was determined. So it just goes to show it is a real problem. So scheduler contention, it's another possible risk that requires careful management. Traditionally, there may be an inherent execution performance risk due to the overhead of the scheduler across multiple processor cores, as called by an application or a driver. Within PikeOS, there exists an independent per-core scheduler, which splits the responsibility of thread management. PikeOS's graphical time partitioning can also be utilized alongside careful design to mitigate this risk. This can further be extended through the assignment of partitions to one or many processing cores. So PikeOS partitioning analysis is provided within our certification kits that I mentioned briefly earlier. And what that does is provide guidance on how best to design a solution with the least impact on system partition switch time. So as operating system objects are also therefore shared resources within the context of a multi-core processor, there is a risk of contention between applications. This could lead to variable impact on an execution time of any partition. Within PikeOS, we include fine-grained blocking to limit critical sections, ensuring coherency of a single OS object. The potential impact of such contention can also be understood through partitioning analysis or through an understanding of the worst-case execution time, which Mark will touch on later in the presentation. The final risk to discuss today is that of IPC contention, so inter-process communication. Depending on the method of IPC utilized, there is a risk that partitions not involved in IPC are still impacted. Within PikeOS, we provide IPC via sampling and queuing ports, which not only isolates IPC overhead to the partitions involved, but also presents no performance overhead whilst that IPC channel is quiet. So as an example or a brief description of these, queuing ports provide a first in, first out IPC channel, whereas sampling ports provide a single message buffer that is automatically updated by a write operation. So to summarize, the use of multi-core processors can create a design challenge due to the risk and therefore requirement for careful management of interference. The interference examples that I've discussed today can be split into three main categories: application, operating system, and hardware. And the good news is that with PikeOS, it's possible to build a Cast-32A compliant multi-core avionics system up to DAL A. That being said, the system still requires complete verification and validation against the relevant standard. So I'd like to hand over now to Mark, who's going to discuss some of the Cast-32A objectives in more detail and explain how LDRA's tools can be utilized to realize this conformance.
Thank you, Joe. So yes, as Joe suggests, we're now going to take a deeper dive into the guidance of the standards and LDRA's product solution. When DO178C superseded DO178B, it was accompanied by a set of supplements reflecting the broadening of technologies and techniques around in the industry. Cast-32A exists in the context of the rest of DO178C and these other documents, and is an enhancement to them all. The Certification Authorities Software Team, or CAST, were a group of civil aviation regulation authorities from Asia, Europe, North and South America, including the FAA and EASA. CAST position papers were for the clarification of issues that related to the formerly established standards in that sector. They covered a range of topics, including the clarification of aspects of the standards that have proven ambiguous and the handling of new technologies. The latter was clearly the case with Cast-32A, the last position paper to be produced by the team. CAST papers generally do not represent official guidance, but they are authoritative, and their advice is often adopted even before it is formally integrated into subsequent published standards. There are 10 objectives in Cast-32A which supplement the DO178C process for multi-core processors through its V-model lifecycle. They span from planning through verification while focusing on shared resources and interference channels. Cast-32A does not prescribe methods for achieving these objectives, leaving that to the systems integrator and their suppliers. Cast-32A has already been superseded by AMC 2193 by EASA in Europe, and will likely become defunct when incorporated into the similar standard AC 2193 in the US. The naming convention used for each of the individual objectives has been carried over from Cast-32A to AMC 2193, making comparisons between the two reasonably straightforward. LDRA has an objectives and requirements tracking system called TB Manager, which allows you to collate the relevant objectives from these and other standards and demonstrate compliance through links to evidential artifacts. We don't have time to walk through all the 10 objectives, so I've aimed to pick out some which are especially pertinent. I'm starting here with MCP Planning 1. As you might imagine, the first part of Cast-32A relates to the project planning process. It discusses the specific items to be considered in planning a project around multi-core execution, such as the device to be used, the number of active cores to be deployed, dynamic features in the MCP, and so on, with particular focus on resource management. It talks about how the processor is architected, what components will potentially lead to contention during verification and validation processes, what issues there are to be aware of, and the identification of appropriate tools. The core 7 requirements that you see listed here are identical in Cast-32A and in AMC 2193. However, in the new document, MCP Planning 1 includes an additional note relating to the independence of testing and explicitly discusses the issues surrounding shared resources and worst-case execution times. This slide shows how external documents and test artifacts are mapped within TB Manager to the objectives. And here we've got a matrix view that shows how progress is shown as the project develops in the matrix in percentage terms. The description of MCP resource usage 1 is identical again in Cast-32A and AMC 2193. It also covers configuration management, overlapping with DIR 178C, which discusses it at more length. MCPs are extremely complex and have many settings that can affect execution and potentially impact system safety. It is important to consider the desired multi-core processor usage patterns, ensuring that all configuration bits are configured correctly such that timing, execution, and memory access work in harmony. The empirical nature of MCP configuration and scheduling optimization makes it highly likely that the configuration will change during development, and keeping track of changing statuses when it does so is particularly important. An automated traceability tool like the TB Manager component of the LDRA tool suite can help avoid a potential project management nightmare in this scenario. This need to trace evidential artifacts also extends to the configuration parameters discussed in the MCP resource usage 2 objective specified by Cast-32A. In particular, the MSR register is central to a typical critical application configuration. This register can set many critical configuration bits, such as the use of cache, access to memory, and hyperthreading. Incidentally, note that hyperthreading itself is not supported by Cast-32A because it adds many non-deterministic effects relating to resource usage. It's therefore advisable for MCP users seeking to comply with Cast-32A to disable that feature at the configuration register level. So that's how it looks in Cast-32A, and conversely, AMC 2193 removes this objective altogether, and instead it defers to the document AMC 2152A instead. However, that doesn't mean the points it raises are disappeared. They are just dealt with it in a different standard, and in fact they're as significant as they ever were. That means that traceability to them, as well as the component parts of this standard, is important, underlying the importance of maintaining traceability to objectives from multiple standards at the same time. Bearing in mind that alongside these, you'll also be tracking objectives to DIR 178C, for example. MCP resource usage 4 is another resource-related objective. Again, this is unchanged in AMC 2193. It highlights the significance of a worst-case execution timing. Consider a typical application with various tasks that run at different rates. The key objective is to ensure that these tasks all have time to finish in their allotted times and can't interfere with each other. Hard real-time systems need to satisfy stringent timing constraints imposed by the nature of the functions they fulfill. Unfortunately, it is not possible in general to calculate definitive upper bounds on executions for programs. Suppose initially that a real-time system runs on a single core processor and consists of a number of tasks running concurrently. The diagram depicts several relevant properties of one of those real-time tasks. The upper curve depicts the set of all execution times, which will naturally vary. Developers must be aware of the worst-case execution time in order to ensure that the timing window allocated to that task is adequate in all cases. Single core processors cannot run multiple processors in parallel and instead use rapid scheduling to make it appear as though they do. For a single core processor, multitasking real-time systems can be guaranteed to hit their deadlines as long as sufficient CPU headroom or capacity is allowed for. Even in the case of single core processors, however, the mathematical analysis of what sufficient means is not soluble in the general case. However, calculations do exist that allow a pragmatic, on the safe side approximation of what that sufficient means. Multi-core processors introduce an extra level of complication in that they genuinely do run multiple processors in parallel. Unlike single processor applications, the task of finding a schedule of X tasks on Y processor cores such that all tasks meet their deadline has no efficient algorithm. Other characteristics of MCPs make that calculation even more challenging. On a single core processor, resources such as memory are dedicated to that core. The introduction of additional cores results in those resources being shared between them, and time-related delays occur as users wait for access. The diagram shows that when a hierarchical memory is shared, interference is possible in many places. These interference channels cause the execution time distribution to spread, so instead of a tight peak, the distribution of execution times becomes wide with a long tail. Outside the realm of safety-critical applications, this issue is of little consequence. But where functional safety and timing are both paramount, it is critical. And what's more, it makes any approach to WCET calculation that is primarily based on an approximated calculation is unacceptable in a world where precision is everything. That said, static analysis does have a contribution to make to a more precise, reliable approach. There are long-standing and proven mechanisms available to measure the properties of software code which are independent of their execution on any particular platform. For example, Halstead's metrics reflect the implementation or expression of algorithms in different languages to evaluate the software module size, complexity, and the data flow information. The TB Vision component of the LDRA tool suite can calculate these metrics precisely. Armed with that information, we can then move on to the recommended dynamic analysis approach, which allows those most demanding algorithms to be exercised in practice and on target hardware using configuration parameters representative of the application under development. It leverages proven technology from the TB Run component of the LDRA tool suite to repeatedly exercise and time the code under test, while stressing the target device simultaneously, as you can see from this configuration window. The LDRA tool suite is able to measure WCET dynamically, measuring the performance of each complete cycle algorithm in turn on a running system. It includes the capability of loading one or more cores, forcing hardware interference to play a part. The slide shows an example of how the statistics are represented in the tool suite, and the graph shows the variation in performance of the same system under differing loads. And you can see that on the right here, we have the long tail in the distribution we referred to earlier. MCP Software 1 is unchanged in AMC 2193. It's also concerned with ensuring that tasks can be achieved in the time allocated to them and that adequate resources are also allocated. It sets the stage for robust partitioning too. Where robust partitioning is unavailable, the WCET analysis features of the LDRA tool suite support the analysis of an MCP application under test, providing evidence of adequate mitigation for interference. Because Cisco's PikeOS provides mechanisms to remove interference risk in terms of resources and time, this clause suggests that WCET can be determined separately for each core. In this case, the dynamic WCET facilities of the LDRA tool suite provide evidence that the features provided by the RTOS are correctly configured to the needs of the application and are therefore mitigating the challenges associated with multi-core processors. The main body of the MCP Software 2 objective is unchanged in AMC 20193. It reiterates the need for data and control coupling analysis discussed in DO178C, focusing especially on the use of shared memory and shared resources. Just to remind ourselves of what that actually means, control coupling is defined by DO178C as the manner or degree by which one software component influences the execution of another software component. And likewise, data coupling is defined in the same standard as the dependence of a software component on data, not exclusively under the control of that software component. The LDRA tool suite includes reports that can be filtered down to provide relevant focus on both data coupling and control coupling. This is an example of a pass-fail coverage call graph. Functions and calls colored green here show where full coverage has been achieved. The notes associated with MCP Software 2 have changed a little to include more emphasis on the fact that interference may occur between tasks of a single component when tasks execute on different cores. Of course, that's always been the case, so nothing materially changes here. There's just an additional focus not to overlook that particular fact. The WCET analysis capabilities of the tool suite are also invaluable in these circumstances to demonstrate that any interference is adequately mitigated. So what have we discussed today? First of all, we discussed the use of multi-core processors and how that has increased in popularity and how Cast-32A guidance can be used to realize a successful and safe avionics platform. We've discussed why interference is an issue and how it can be mitigated through the use of PikeOS powerful features. We've taken a deeper dive into Cast-32A and AMC 20193 objectives and pertinent differences between the two. And we've taken a look at how LDRA's tools can be used to ensure and demonstrate conformance.
I would like to thank Joe and Mark for their informative session. I'm sure this webinar has helped our participants understand the multi-core challenge, a practical approach to Cast-32A and AMC 20193 compliance. And thank you to everyone for joining us. It was a pleasure being with you today. And that just leaves me to say thank you again, and we'll see you next time.
Thank you all. Bye.
Thank you. Thanks, everyone. Bye-bye.
Bye.